Hello there, welcome to another problem session. So today, instead of doing a particular problem, we are taking time to address the relationship between a static electric field and static electric potential. So this word static here is very important. What it means is it's an electric field of charges which are fixed. They're not moving. Okay, so say you have a positive charge here, and so we are in a in a frame in which we say put a frame here, and say this thing is origin, and so this charge is not this charge is fixed there, it's not moving. So V of this is some Q is actually 0. Of course, if I have a frame which was some other frame which is moving through this frame, this charge will be moving, and so we're not talking about that situation. So when this velocity of this charge is 0. So in that case, what happens is electric field at any point is pointed away, and for this charge you find that over here electric field is pointed that way, over here the electric field is pointed that way, over here electric field is pointed that way, electric field is pointed that way. So if you go all around, it's the same magnitude electric field at the same distance from the charge, and if you kind of connect them, you have electric field lines. So this one line, another line, another line. So these lines of electric field, the space around this charge can be characterized to have these lines going through them. So we call it this charge, if you remember this charge, we call it source charge. And these are electric fields, E field of the source charge. Charge Q that's located at O. Okay, so we don't say the entire thing, but that's understood. So always a source charge. Now, if I had a this is my frame, and if the charge was over here, and V of the charge is equal to 0, so this doesn't have to be at the origin, it can be at some point A, and this is where the charge is located, and this is a positive charge. Then again it's going to be symmetric about this, just like this, as if so it is not a matter of the charge's origin or not at the origin. Is electric field are going from the charge all around it. Okay, so like over here is pointing the negative towards the negative x-axis, although the point is at the positive. Over here the same point you can see is on the right of the charge, so but this point is to the left of the charge, and so the left part is going to the left, electric field is going to the left. Electric field lines of this charge of charge Q at P, source charge Q at point P. Okay, so if I have more than one charge, these are all static charges. So this is static because this thing is static, this is static, so this thing is static. So an electric field is a vector quantity. It turns out the static electric field have a important mathematical property. Okay, so if I go at this point, say P, and I look at the electric field, of course, it depends on this. From the charge, this vector, I can write this vector. I can write this as a function in terms of this vector, or you can say x, y, z. So you can write this as an electric field at point x, y, z. And of course, here the location is at the origin. So over here, say at the same point P, let's call it point P over here, point P, and it's still x, y, z. And this one is x, q, y, q, z, q. That's where the, over here, the located at x-axis, so to say, but it could be anywhere. So if I look at the electric field here, you would be writing as a function of x, y, z, and this is fixed. So it's kind of like a constant. This one can be anywhere, can be anywhere, but this is fixed at the location of the charge. So this is kind of fixed. That's why we mean static. Okay. So this is a function. So you can see it is a vector. You can write it actually three functions. You can write this as a x component at location x, y, z. It's a collection of these. Y component x, y, z. Z component x, y, z. If you write this in a Cartesian, you can similarly write this in a spherical coordinate, cylindrical coordinate, or any other coordinate system of your choice. Okay, but normally we're going to talk in terms of Cartesian coordinates, sometimes spherical coordinates, or sometimes cylindrical coordinates, but mostly Cartesian coordinates. So the property that these functions have is if this is static, del cross E equal to 0, so-called curl of electric field is 0. So you might say this is a law of nature. For a static electric field, you have this. So from mathematics in Calc 3 or something like that, you would think that the electric field can be this means electric field can be written as a gradient of a function. Normally we write like this, and you can always you can see that this can be some v plus some constant will also be the same thing, right? So v will be defined up to a constant. So this is v is a function of x, y, z. So this is x, y, z, and v is a function of x, y, z. So if you plug this in here, this will be an identity. So b is a scalar function, meaning unlike the electric field, which has three components, v is just one function. Knowing one function gives me all three functions if the electric field is static. This one function is called electric potential. So this v x, y, z is electric potential at say point P at x, y, z. Because this is a constant, its value is relative to some reference. Okay, so this is relative to some constant reference. Say at v0 at some reference point, y reference and z reference. So this will be some constant value. So if this is at this point I say is 0, say v equal to 0, then we just normally it's supposed to be at that reference point you set v equal to 0, and then kind of this fixes all the potentials at all other points. So this is like a mathematical relation, but what is the physical relation between the two? Okay, and a lot of time in the introductory courses you start from physical relation and then you get to the mathematical relation. Let me actually before we close up mathematical relation, we can write this also, these two together, if as an integral. You can so if I have some place A to some place B, and if I integrate along this path A to B, then I can write V at B, let's call it X, Y, Z at B, and this is X, Y, Z at A. So V at X, V at B, let's call it V at B with this coordinates, minus V at A is actually just integral point A to B E dot dl. dl is a line on this path. dl is a small vector that goes along the path, and you can do it over this path or that path. Is a path independent, but it has to, we have to pick a path to actually do this integral. And this is this important relation. This relation is actually same as saying that del cross E equal to 0, and we're going to write E as this. And so if I know electric field, I can actually get the potential difference. And we're going to use this to generate our physical interpretation of the relationship. Okay, so the way we're going to look at the physical interpretation is when I address the question that this whole place is filled with electric field, and you have a point A, and you have a point B in space, and we are going to take a test charge. So take a test charge and move from here to there. So if I want to move a distance dl, you know, on the test charge, the electric field may be at this point, electric field may be pointed that way. And so, and let's say test charge is positive, test charge Q is positive. So force on Q, you may remember, is Q times E. So the amount of work I will do in moving on this distance dl, work on the dl will be, this tiny amount of work will be F. This is the force by E field, right? And so I want to move it, so I will have to, particle will accelerate naturally, right, because of this force. So I will have to apply force, so this will be minus F by me. So the force I will apply, force by me, in order to prevent the acceleration, will be minus Q times E. And so the work by me will be F by me dot dl, and so this will be minus Q E dot dl. So this is for dl, so let's call it dw. And so the net work from A to B, when I do the net, so W A to B by me, so work I'll have to do, which will be the amount of energy it will have here compared to the amount of energy it had over here. So this would be equal to minus Q E dot dl, and you can bring the Q out there. So Q times I have to go from A to B, and I have electric field dl, right? So per unit of the test charge that I need to do work on, so work by me in going from A to B per unit of test charge. So this is the work per unit of test charge is actually equal to minus A to B E dot dl. And lo and behold, what is that? That's the difference in potential between these two. So this is the difference in potential. This is equal to actually VB minus VA. So work I did increased the energy. So the potential is how much work was done per unit test charge. So for the entire test charge, we say at B there is a potential energy, and we write symbol U. UB is equal to UB minus UA. So at compared to at A of charge Q. So this is the difference in potential energy in electrostatic potential energy. So we have everything is static here, is equal to this thing that we with Q minus Q Q times VB minus VA, which is minus Q integral A to B electric field dot dl. So this is the relationship. Okay, let me summarize the physical thing. Physical thing is electric field actually is related to electric force. So at each point, if I put a test charge, how much electric force the test charge will experience. And of course, by balancing the force, I can figure out how much energy I need to put if I move the charge along this. Okay, so if I move the charge from A to B, how much energy do I need to put? When I calculate that, I find that the energy per unit charge I need to put is the change in potential energy, and which is this integral I can get from the electric field. So this is like a work integral of the electric field that I need to do to figure out the change in electric potential. Now, electric potential is not giving me electric energy because it is not work, but in a work per unit charge. So I need to multiply, and that thing we call it electric potential energy. The only thing I can get is a difference in electric potential energy. So if I picked A to be 0, then I will have this formula that we can obtain. Let's do a simple example. Okay, so suppose I put this is the source charge. Source charge is at the origin, and we want to know what's the electric what's the VP gonna be like. Okay, so all we can do is BP, pick a point A, and from A to P we do this integral because we know the electric field. So here the electric field at any point, so electric field is simply k q over any point in arbitrary point which is distance r from here, and this is r hat is the directly outward vector r square. Let's call u hat r, u hat in the r direction, okay, unit vector. So this is the electric field. You should remember this, okay, because this is in a radially outward direction, tells us what kind of path to pick. Using, this, we can use a path as an arbitrary path this direction. So the path I pick is, I'm going in the angular direction, perpendicular to this is perpendicular to r hat, u hat r at all the points, okay, and then I go along the radial direction. So this is from A to P. I go to A to B first, and so when you do this integral, if E is perpendicular to dl, then E dot dl will be 0. So minus E dot dl, A to B in this case will be 0. So A to B is, I get a 0. From B to P, E is parallel to dl. So E is that way, dl is that way. Then E dot dl is just E times dl, and E depends on how far we are. So dl is just a dr. dl is dr. So this is E times dr. And E at any point is this quantity, which is kq over r square dr. So when I do the integral minus integral, so v at P minus v at A equal to integral A to B plus integral minus of this thing, right? Minus A to B and B to P E dot dl. And this is 0, which already agreed. And then this is kq over r squared dr, and rb is same as ra, so I go ra to rp because the integration variable is now all set. So this is equal to minus kq minus 1 over r, integration this just 1 over r, ra to rp. And so what do we get? We get kq over rp minus kq over ra. Now if I want a simple formula for this thing, then we would want this to be somehow 0. So we'll pick a so that this part is 0. And so we'll say pick, so this is my choice, pick A at RA equals to infinity, far away. So I'm going to pick way out here. So A will be here instead of over here. If I do this, then I see that VA I can pick to be 0 there, and then with this reference, this is my reference, this is reference. So the V at any point P is equal to KQ over R at P, Q at origin. So that's the formula we get for a source charge at the origin. What if the source charge was not at the origin? Let's do that out. Okay, now we have a case where source charge, same source charge, but not at origin. So origin is over here, and source charge is here I just put x-axis, okay, for simplicity. So what's the V at P? We already noticed that reference, so we know that if source at origin and reference at r equals to infinity, reference 0 V at infinity, then V at any point P is kq over how far away from the origin. The r is the origin to point P direct distance. So this we know, we just figured out, okay? So in this case, all we need to do is find this distance, right? That's the direct distance. This is the r, and this r here is square root of x minus a square. We might just call it x at q, y of q, z q. Let's call it x q plus y minus yq square plus z minus zq square, and just copy this formula. So V at P here is with this r, it's going to be kq with this r. You might call this r, usually this is the thing that's used, the symbol r. So this r we can just call it some other symbol, maybe you just call it like this kind of script r. So it's a distance, direct distance. So if we call this distance a small r, then this distance we can just use a script r just to distinguish. We have to go from charge to the point P. And notice that I don't need to worry about this vector direction, things like that, because this is scalar. No need to worry about direction, vector direction, when we work with potentials, electric potential instead of field. But we don't have Gauss's law to help us here, okay? So there's no Gauss's law for electric potential. Gauss's law is for electric field. So there's a little bit difference in terms of what technique you'll use and what circumstances, but in most cases, electric potential is way easier to deal with, because a lot of the time you are thinking in terms of energy, and electric potential gives it's not energy, but gives energy of something if I had to place a charge. So if potential was this over here, for energy we need to do what will be the energy, what will be the energy of another charge q if we place this charge q at P, okay? So this actually, what will the electrical potential energy, and that will be q times kq over r. So that will be, because I can multiply q with the V of P to get the energy. So this is the energy of this charge. U is not of source charge q, but that of the test charge q. That's how we deal with it. Now the formula turns out to be, if you, the source charge and the test charge are like an equivalent position here, right? But it's just a coincidence because we're dealing with one source charge. Okay, let's talk about if I had two source charges, what will be the electric potential? Okay, so now we're going to address what this will be. Okay, we know this source charge will have its electric potential over here, V at P for 1, and this will depend on this distance, and this will depend on this distance, and this will produce V at P at 2. So V at P net is just actually algebraic sum V at P of 2. And these formulas we figured out with reference V equal to 0 at R equals to infinity. V at any point is equal to K Q over R. So the R is the direct distance. We can put a script R. So we have, this is the formula for any charge. So this is just simply V equal to K Q1 over R1, no vector, just this positive and negative number. If this is charge is positive, it's positive. If charge negative, it's negative. Plus K Q2 over R2. So we can ask same kind of question. Potential energy of a, so if I place a test charge at P, okay, a test charge of this amount, then what is its electric potential energy? Okay, that just be Q times V at P, whatever the net is. And so that's the formula here. Now Q, KQ1 over R plus KQ2 over R. Now this definitely says these are the source charges, these were the source, and this is the test. So this is a two source charge. How about if we have a charge distribution? Okay, so suppose we have done a situation similar to this for electric field. Suppose we had a line of charges, and all we could do is give you a charge per unit length, and say this is some constant. So the total Q total is lambda times L. So how would you get this? Well, it's the same technique you're learning throughout, is to divide this thing into little tiny pieces and look at one of those representative pieces. So say this is a symmetric line. Point P is 70 point. You can have a point P over here, but that's going to be a harder calculation. But suppose you do it like that, some distance D from the center, and let's call this x-axis, and let's call this y-axis. Then this little dy will have lambda dy will be charged over here, and this distance will be what it will, so it will matter. So this is R will be square, this is y, the square root of d square plus y square, right? And from this, the potential from this element will be just K amount of charge is lambda dy over square root of d square plus y square. So if I want to do the net, Vp net will be just this integral, integrate this K lambda dy square root of d square plus y square. The dy is collecting all the charges as going from minus L over 2 to L over 2. So this integral goes minus L over 2 to L over 2. And what's the reference? So when we wrote this out, implicitly we assume the reference is at very far away from these charges, R equals to infinity, okay, where V is 0. So this is the reference, and that's why we wrote this formula down. And so we can integrate it, And this integral is very much simpler compared to electric field integral. Okay, so I'll just leave this for you to do. This is not very difficult integral to do. Okay, and it will this would not be lambda L k lambda L over d square. It's not going to be like this, no, d, not going to be like that. Okay, so as if you can't put all the charges over here and then say there's the same potential. No, because the charges are different places. There are many other problems we can do, many other problems, other charge distributions. Of interest. One would be like if I have a disk of charges and the point P is over here, what it will be, okay, or the ring of charges, and maybe point P is right on the axis, maybe point P is over here. That's much harder. You can have a sphere of charges, maybe a spherical shell, and this is very important. Charges are just on the shell. What's the potential over here? What's the potential over here? Then this VP is not necessarily zero. Okay, and so you have a P1 and P2. So unlike electric field, the electric potential is not zero, because once you assume electric potential over there far away is zero, then by saying inside will be zero means electric potential over here and here the same value. So you're allowed to choose one reference point. You can't use the reference point here and here. Okay. The other cases are very similar. You have a complete solid sphere, and what's the electric potential inside, what's the electric potential outside. So some of these examples we're going to do in the future. Already the video is almost 37 minutes long, 38 minutes long. So I'm going to stop here. Let me know if you are wanting to have some particular electric potential problems solved. From the next video, I'm going to start solving electric potential problems. Okay, so I'll talk to you later. Bye.